Studies for giving me an opportunity. And I thank Pradhan Madam and Prasad Madam, who were instrumental for syllabus framing. I'm very happy to be a part of it. Okay, so if it would have been a student group, I would have put up the question, no answers. If it is faculty group, so I've kept the answer open just to save some time. So I'm going to share some of the methodologies which we follow here. So at classrooms, it will be of very good use. Like Patil sir, he said, it's better to start with some case studies and all, industry applications. So which country gave the citizenship to first humanoid? Okay, so we should be like knowing the current trends so that we can inspire the students. So in 2017, okay, you know about Saudi Arabia. Saudi Arabia has less manpower, okay, because they don't have resources. Like, so if you don't have resources, there is a problem always, but they are finding some solutions. Mostly they want foreigners to come and work in Saudi, right? And because of this AI, okay, moving towards humanoid, Sophia robot, you all would have known. So the first citizenship for Sophia is given by Saudi Arabia. Okay, so it is like legal personhood. So Saudi is thinking, foreseeing, having a vision, like in future, most of the work will be done by humanoids. Okay, so you can understand how much this subject becomes important now, right? And we were discussing about who is the father of AI. Okay, so always we talk about Turing, but Turing test, we know just now in first session the speaker has elaborated what is Turing test and all. Okay, so we know Turing, but Turing's follower, okay, McCarthy, okay, he is the inspiration for AI. He has coined this word also, AI. And if you read these words, any aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So the meaning is, if you are able to precisely define some feature of intelligence, definitely you can simulate that particular feature. Okay, this is what John McCarthy he said. But unfortunately, his dreams he couldn't continue. When he resigned, he could not continue. Actually, even he became the father of AI after his death only. That is a sad truth. Okay, certain things in history, if you say you can inspire the students, because teachers are here to inspire students, right? And this is like two things. One is history, one is the latest things. So we always have to say to the students, right? We should not forget the history, and we should not be away from the current happenings. So the current happening or the latest, which everybody has to know, is company that created a processor that works with the help of AI. Okay, so you know CPU, GPU and all. This is TPU, Tensor Processing Unit. So we all know Alphabet is a parent company of Google. Alphabet has many products, right? Like you have Google Maps, many things, right? Your Android also. It has created a processor that works with the help of AI. Okay, so that's why you are able to get your Google Photos and other services very smartly. Okay, advertisements, search, everything is because of this TPU. So students will understand, okay, more than CPU, GPU, you have TPU, and TPU, what it is, they will search, they will understand many things. Okay, creating curiosity. Okay, so now I am jumping into the course outcomes. So generally all the course outcomes contributes, right? So it doesn't mean, or I cannot say like I teach one unit, I achieve one outcome. Okay, the whole course actually helps in achieving all the outcomes, even though preferably or in priority, some of the outcomes you may expect more with some of the units, but still I always emphasize the whole course contributes to some outcomes. When the student entered your class, they don't have these attributes. They don't know how to identify suitable agents. They don't know how to build a smart system. They don't know how to identify knowledge associated with ontological engineering, how to plan a strategy, how to solve a problem, how to apply suitable algorithms, how to implement ideas. They don't know, right? How to represent complex problems. They don't know. Okay, so at the end of the course they will attain all these outcomes. Okay, so because of teachers and books syllabus, they will attain all these outcomes. So in unit number 3 and 4, the major focus is on CO3 and CO4. It doesn't, again I emphasize, it doesn't mean that only these outcomes are achieved. No, this learning of unit 3 and 4, which is very crucial for other outcomes also. Say for example, outcome number 2, it supports you can build a smart system, right? So it helps actually. Fine, so I'm just moving ahead. So unit 3, what we are going to talk about, it is like 7 hours. No, you need to spend 7 hours in your lecture time to say these concepts. I'm going to take very few minutes to explain it, so in a teacher's perception and with examination perception. Fine, some of the pedagogy I'll share. So this unit has game theory, optimal decision in games, something called as alpha beta search, okay, which is like min max search, you know, or you don't know. I'll just quickly say that. And Monte Carlo tree search as a small bit just introduced, and stochastic games, partially observable games, because it was discussed just now by the speaker one, and some of the limitations you have, and CSPs, constraint satisfaction problems. So complete, this unit is so interesting. Okay, from unit 2, problem solving has started. Now we are in the competitive world. When you say adversarial, it means competition. Okay, I compete. Okay, it is not, even though you say competition, no, children sit separately and they compete with the computer only, right? So they don't play together. Okay, so even though opponent, they want opponent to be a person who is away from them. Okay, so somebody, okay, maybe you can take an example of chess or a tic-tac-toe, right? So these are examples for adversarial searches where you have more than one agent, or one agent and one human. Okay, there is a competitive environment. So adversarial means competition. Somebody wins, somebody loses. It is, or it may be a draw. So if you win, you say it as +1. If you lose, you say it as -1. If you draw, it is 0. In some of the notations, they say it as half for draw. Fine. So the environment with more than one agent is also called as multi-agent environment. I'm just repeating what Prasad madam, she said about single agent and multi-agent. Okay, so you would have seen such robotic soccer matches. Like 20-second soccer match was there in the previous year. So maybe we can prepare the students for this also. They can develop a robot which can play a soccer match. Okay. So game playing is the first topic. Okay, so why do AI researchers study game playing? It's a good reasoning problem. Okay, because you have some methodology. You know how your mind thinks. Like McCarthy, what he says. If you understand the features of reasoning, then definitely you can build a system which can reason like you, which can think like you. So as a human being, whatever moves are in chess, whatever moves are with tic-tac-toe, we are able to describe the features. We are able to describe the moves. Okay, so it is a good reasoning problem, and formal and non-trivial, right? And hence direct comparison with humans is very easy, and hence game playing becomes important in AI. Okay, you know sequence of moves, you know the rules, you know the how much payment. Some games have payment. Payment may be a score or payment also. Okay, there are different terms used here: utility function, payoffs. Okay, all means the same. So objective is to maximize the payment. Okay, so some of the points you need to remember here, like states, what is the board you have, what are the initial states, what is the successor function, how you will complete the game, what is the end point. Like in chess, if you capture the king of the opponent, end it is, right? And then utility function, so what we discussed just now. So these points have to be known. So, so for example, here, if you want to discuss on tic-tac-toe, I'm just moving to this portion of my slide. I'm just sharing an Excel sheet because I said like some of the pedagogy to use for your students, it will help. So maybe it will, this may help. I'm just putting a sheet 2. So whenever you teach to the students, you can take a tic-tac-toe here. Okay, so 3 by 3 matrix, if you can take, then it will help them. So what is tic-tac-toe? We all know, right? If the students don't know, also we can say you place X, the opponent keeps a O. Okay, or you keep a coin, the opponent keep a different paper maybe, right? So we play it on a board also, on a paper also, right? So
Hello.
yeah.
Yeah, sorry for yeah. Actually, your screen has suddenly
Okay,
stopped
okay. Stop
being
that. What?
shared.
Just a minute. Huh?
Yeah, just now it happened.
Okay,
So
okay.
nothing to worry.
1 minute. Huh? I'll stop sharing. Again, let me share. My Excel sheet was visible? No? Is it visible?
Yes, it's visible now. Now we are on an Excel sheet.
Yeah, yeah, yeah. So just now I have drawn this much only. I'll just, okay, move to the new sheet. Okay, so whenever we teach tic-tac-toe to the students, we may take an Excel sheet, because in online teaching that will help also, right? So tic-tac-toe is a 3 by 3 game where a player places X and the other player puts a O. Okay, win is determined when you have X on one side, or on the row side, or on the diagonal. Okay, so I think I have kept a 4 by 3, I think. Okay, now it is 3 by 3. So when you teach the students, it will help actually. You can, I can zoom this so that it will be useful. Zooming, some problem is there. Okay, fine. So now here, when you have an X, so then you can see all the possibilities actually. Suppose if it is going to be tic-tac-toe, the first position you may have, initially the board is empty, right? So the opponent, the person who plays first will try to maximize his potential to win. So how many different combinations he may have. So initially, let us assume this board is empty, right? I just copy this here. So you may say like how many combinations are there, okay? So to make it interesting for the students. So you have so many combinations, right? So maybe you may have a X in the first row, first column, X in the first row, second column, X in the third row, means how your brain thinks. Okay, so when we play, should we have to start in the first row, first column, shall we put it, or shall we start with the second row? Okay, shall we start with second row? Similarly, it goes on. Okay, I'm not going to draw all the things. So maximum possibilities in all the 9 cells, right? You may put X. And then when you take one subcomponent, okay, let us assume you are starting from this only. Okay, let us forget about all these points. Okay, we'll forget about all these points. Let us assume that we want to explore this possibility only. So what possibilities the next person will have? Suppose if I am playing, I'll try to maximize my winning proportion, and the opponent will try to minimize my winning proportion, right? So how the moves will happen from here. So after my X, the opponent will try to keep a maybe a O here, okay, or he may think to keep, sorry, okay, he may think to have a O here, okay, or here, next one, right? So instead of here, he may think to have a move here instead of here. Okay, so maybe in a diagonal, he may feel like, oh, again, she may keep X here. So like this, there are many possibilities, right? So I have taken this one alone, right? So the children of this is, it goes on like this, right? I have explored only one probable child, one probable child. Okay, similarly you have so many moves, right? So if you choose this, then what are combinations? If you choose this, what are combinations? So if you see here for tic-tac-toe, it is like 9 factorial. Okay, because you are starting with this one, right, empty, and you have 9 positions. So there are possibilities of 9 factorial combinations. Okay, 9 factorial means it is like more than 3 lakhs. Okay, which is like very difficult. and hence we need to go for some strategies. Okay, I hope this you would have understood it. And this topping sharing, I'll be switching here and there. Moving to the presentation again. Okay, so now this is what I tried drawing. Okay, so because of time, I just wanted to say you Excel helps a lot in teaching the students lively. So the computer can be maximum player, or you may be a maximum player. The opponent is minimum. So the main aim is one person wants to win, the other person tries to minimize the probability of winning of the opponent, right? So like this it goes on. Finally, you get into a conclusion. Like somebody wins, somebody loses, or it may go into a draw. Okay, if you can see here also, you can see this, right? Terminal is somebody has to win. Okay, fine. So now I was talking about, I just started with adversarial searches, right? And then I moved to game playing and an introduction with Tic-Tac-Toe player. It will help the students to understand quickly. And then the next topic is on alpha beta search. Okay, when it comes to alpha beta search, because I saw with my statistics, like many of you are beginners also. So quickly you should know about what is min-max. Okay, so when you say min-max, so like what we talked on tic-tac-toe, one person tries to maximize, the winning chance. The opponent tries to minimize the winning chance of the other person. Okay, it goes on. So if you have two players A and B, A wants to maximize his chance of winning and minimize the players B's chance of winning, and B tries to maximize his chance of winning and tries to minimize the opponent's A's chance of winning. Okay, so this is what min-max is. So how to understand this, how to replicate this in a tree format. Okay, so I'll just share this also. My screen is visible. Can you say, Yusuf?
Yes, ma'am, it's visible.
Jamboard is there?
Okay. Yes, ma'am.
Yeah, so I'm just going to quickly say like how you will understand this min-max algorithm, right? So sorry for my diagrams. Okay, so here, because whatever I can do here, I'm trying to explain a small example. I'm just putting okay. So let us assume you have, this is a problem of min-max. So actually in syllabus, you don't have min-max, but unless you know min-max, you cannot work on alpha beta. Okay, you should know the problem of min-max. So we need to teach this strategy. Okay, so min-max strategy we need to know, then only we'll be able to teach the students alpha beta. Okay, so now here the min-max strategy. So I want to keep here something like max. Okay, so this is max node, and I want to have a min node. Okay, so this is min node. Okay, and this line. Okay, is maximizing line, and this is the minimizing line. Means these nodes fall under minimizing criteria, right? So again, I will draw this. So here I have some leaves, so maybe like this, and I have something like this. Okay, so the triangle, the shape represents what is maximum and what is minimum. Okay, so here again I may have one more maximum. Okay, so this layer is also maximizing layer. So three layers you have: maximizing layer, minimizing layer, and maximizing layer. Now here I just wanted to okay, so here let us see. I want to put some values here. Let us assume that you have a value 2 here and you have a value 14 here. Okay, so what this means is, okay, let me connect all these branches. Okay, so you are aware of different strategies. Okay, so now these are the possible moves. Okay, so when you play chess also, you try to understand, okay, I move this pawn. Okay, when I move this pawn, what my opponent will do, he will cut my pawn. Okay, there is a chance. Okay, if not pawn, If I move my queen, what will happen? Okay, then I have a chance like he may kill my queen or he may take my horse. So we try to go in different levels, right? So I try to predict my move. I try to visualize my different moves. Okay. Also, I try to predict the opponent's moves. I know that I want to win him, but I know that he wants to make a loss on me. Okay, so he wants me to lose. Okay, so I know when I keep a coin, what will be his next move. I'm trying to foresee. So it goes in depth, right? Depth first. If I keep this, he will cut this or he will do this. If I move ahead, so like this it goes. So the problem is we cannot think much deeper. Okay, how computers helps us, because it goes to various levels. That's how it is interesting for the game player, right? Okay, now let us assume that you have taken a move. Okay, and so finally you have leaves like this 2 and 14, and here you have something like -1 and so check out these leaves 2 and 14, which is maximum. Okay, 14 is maximum, right? Okay, a maximizer will maximize, right? So it will go here. So you will have a, sorry, here it is minimizer, right? So sorry, this is 1 minute. One minute. I just want to erase this. I think it got struck. Okay, so 1 minute. I think my screen is not visible, right? 1 minute.
Yes, I will stop.
1 minute. Sorry for that. I made a control Z and everything went. Okay, so quilts, okay, means challenges. Okay, so let us assume that you have a maximizing node and you have a minimizing node. Okay, and you have some leaves. Okay, so fine. And you have something like this, and I will just put a value here. Let us assume you have something like 1. Okay, something like 12, and you have 2, some values like this. Okay, let us assume you have -1 and something like 15. Okay, and all these nodes are connected. Okay, all right, connected. Okay, so connected, right? So this is like you are maximizing, and this is maximizing and this is minimizing, right? So I drew something wrong here. That's why it created a problem, because this is leaves, right? So I should not write here. Okay, so this is a root. Okay, this player wants to maximize and this player wants to minimize. Okay, so it's better you may have some other representations here instead of triangle. That is better. It will avoid confusion. Okay, so now here, out of these two leaves, which you will choose, it is minimizing layer. Okay, in minimizing layer, in this layer, okay, I'll use a laser. In this layer, you will choose a minimum value. So what will be the value? Will it be 12 or will it be 2? So it will be 2, right? So because it is a minimizing layer. So this node has 2 now, right? And if you see here, among these, which is minimum, Of course, -1 is minimum. So this layer is the minimum layer, right? So it will have minimum values. Okay. So then here you will have a value -1. Fine. Now when you come to the top layer, okay, so in this layer, it is a maximizing layer. Okay, so he is player A, he is player B. Okay, player A always chooses a maximum for his profit. Okay, so among 2 and -1, what he will choose? Definitely, no doubt, a maximum value he will choose, right? It will be 2 definitely. So the meaning is the which path would have been traversed? This path, right? Okay, 2 means this path is chosen. Fine. So this is your maximum algorithm. So when it comes to maximum algorithm, the complexity is more, like Prasad madam's final slide on complexity, right? So it is order of b to the power of d. Okay, so b is the number of branches you have and d is the depth. So in generally in chess game, the average move is, okay, if you have if you count, like for example, when you start the game also, when you move the pawns, how many combinations you have, you can move the pawn in one place, means one square you can move, or you can move to 2 squares, right? So total 8 pawns you have, so 8 into 2, 16 combinations. Then similarly other combinations, you may move horse to the left side L or to the right side L you can make, right? So like this, an average number of moves is 35. Okay, I'm talking about the starting position, but in the middle it will be more, right? 35 positions you can move, branching. And every player have a chance of moving 50 in depth. Okay, so there are 2 players, so the depth will be 100. So you can imagine so much of complexity here, right? So such a complex problem is very difficult to solve, and hence from min-max we move to alpha beta. Okay, so from min-max we move to alpha beta because of this issue. Okay, so I'm just erasing this so that I can write something with respect to alpha beta. So alpha beta, what is the advantages? You can reduce or you can prune some of the useless nodes. Okay, when you know something, okay, anyhow this is going to be maximum, anyhow this is going to be minimum, then why to explore other nodes? Okay, that's why it is very interesting. Okay, now here if you see this movements, okay, I'm just writing here. Okay, so the first time when you know 12 and 12 is the first value, right? So the first time when you see 12, when you go and see 2, you know that this is minimizing layer. In a minimizing layer, the advantage is you understand that the value is 2, right? Because only 2 nodes are there and minimum value is 2. When you climb up, you understand that anyhow this value will be, okay, greater than, because it is maximizing node, right? Anyhow it will be greater than or equal to 2, right? Without exploring this right side. Okay, without exploring this right side, I come to some conclusion. Okay, I'm trying to say you in a very simple way. Okay, with only 2 layers. If the layers are more, then again the problem will be complex. Okay, so now we understand that this node, okay, we want it to be greater than or equal to 2 without exploring this, right? So I just move on here. When I move on here, I get a value which is -1. Okay, when I get -1, I understand anyhow this minimum layer will have a value which will be less than or equal to -1. Okay, so should I have to go and check this? No, because my maximum value anyhow it is going to be greater than or equal to 2. So why I have to lose my time, okay, in searching the right side. Okay, so the aim is when you understand you are going to have a value greater than or equal to 2 by exploring left hand side. Okay, then there is a possibility to prune some of the branches. Okay, so I will not explore it. I know that I want to conquer queen. Okay, if I take this part, I will miss that chance. Okay, I will not get that much importance. I will not get that much points. Okay, so I will not explore this path at all because I know that the opponent is going to minimize it only, okay, which I am not interested, right? So, and hence this path is chosen now. Okay, fine. Okay, so now I'm just stopping sharing this. Back to the presentation. Okay, so I'm going in deep now. So it is called as alpha beta search, where whatever I discuss, it is there as an algorithm. Okay, so finally you terminate whenever alpha is greater than or equal to beta. Initially, you will have alpha as minus infinity and beta as infinity, which will be like checking parameters. Whenever, because alpha is a maximum value, right? Beta is a minimum value, and you have to initialize in the reverse way. Okay, alpha is minus infinity, which is the lowest value. Beta is the highest value, because you want to come to a conclusion like alpha will be greater than or equal to beta at a particular time, where you will not explore that true nodes and you will prune it. Okay, so like this. So if you see here also a simple example, because this presentation will be shared, Part cursor he will be sharing with you, so I thought like it will help. Okay, and hence I've kept some presentation with respect to this problem also. So this, as we discussed, this is maximum layer, this is minimum layer, this is maximum layer. Okay, so I took 2 layers only because we cannot draw so much, right? And these are the terminal nodes. So as you know, here 2 and 3, so maximum 3 is chosen, right? So alpha is kept minus infinity, beta is kept infinity. So it is propagated. And once you see 3, okay, 3 is greater than alpha, which is minus infinity. So alpha's value changes to 3. Okay, and similarly, if you see here 5 and 9, the maximum value you have is 9. Okay, so okay, so here, because it is alpha beta, right? So it moves on here. And when you see 3, 3 is propagated back. So you get a 3 here because minimum value is 3, right? Because among this, you will have a maximum, right? 5 and 9 maximum will be, you will have 9. Okay, so between 3 and 9, you will have maximum as, minimum as 3. Okay, so here alpha is not greater than beta, right? And hence you explode. Otherwise, you will not explore this possibility, right? So you need some time to just watch this, understand it. Okay, so because before telling to the students, you need to work out, then only it is possible, right? So then you can see like here how pruning happens and how here pruning happens, because alpha becomes greater than beta. Here 3 is greater than 1 and hence pruning happens, right? So finally, which path is chosen? This path is chosen. Okay. This green color indicates which path is chosen. Okay, so if you carefully see it again, definitely you will understand. If you would have understood the math with 2 layers, this will be easy for you. Okay, so I have kept a simple animation for you for beginners. In classes also you may use this no, possibly some animations, because nowadays kids have a lot of habits with animations, right? So let us assume you have 0 and -1 in min-max algorithm. Okay, so you will have 0 here, it is maximizing node. Let us assume the second node with 0, and you have 1. So this is a maximizing layer, so you will get 1 here, and this is a minimizing layer. Between 0 and 1, it will choose 0, right? So exploring the next path, it goes to the left side like a depth first search only. It goes to the last node and it sees the value -1, and it sees the next node, its value is -1. So automatically -1. Okay, maximum is -1 because both are same. Okay, so it does not have possibility, so -1, right? And then it goes to the last one, tries exploring this with the depth first. You will see a -1, and here it is like -1 again, and this is -1. Okay, so this will be -1. Okay, there is no doubt. And when it explores here, you will see a value which is 1, and you have value -1, right? So maximum of all these 3 values is 1. Okay, and minimum of -1 and 1 is -1 here. And again, this is maximum of 0, -1, -1, so 0. So this 0 is taken. So this comes to this path, okay? And hence you can understand how to choose a path, right? So that was the topic, which is over. So without min-max, you cannot teach alpha beta. So you need to teach min-max and then alpha beta. So by using alpha beta, what is the advantage? You reduce it. Order of b to the power of d becomes order of b to the power of d by 2 at least. Okay. So then comes Monte Carlo's tree search. Generally in games like Go, it is used. Okay, as it is using reinforcement learning, also principles of machine learning it is using, and heuristics and probabilistics. Okay, so here, because it includes a lot of complexities with mathematics, okay, even in the book it is not given. I've taken from some websites only, okay, and those websites I've kept at the end. You may go through it and check out. So you would have seen this game, right? Okay, this game, Mario, it uses Monte Carlo algorithm. Okay, so where you have no mushrooms, you have flowers, leaves, no, different birds. Okay, so different possibilities. Okay, so this game uses, so like our board of studies, they were emphasizing. So students should know where it is used, and hence with that thought, I've taken this, right? So you can go through it. Alpha goes 0, it uses, but still the challenge is open only. Students who are interested can participate, as it is using convolutionary neural network, which is not part of third year syllabus. You need not go into detail. Okay, so just an surface view, overview they should know. Okay, later. So, and on what concepts it works? It works with back propagation, like what we saw in min-max, what we saw in alpha beta, back propagation, selection, expansion, simulation, and back propagation. Okay, so we know what is selection and what is expansion in breadth first and depth first also. Okay, how you go to the deeper way. Okay, like this, right? So same concepts. So when you go deeper, okay, how do you expand nodes? How do you simulate all these environments? And how do you back propagate, right? So that much is expected with Monte Carlo games because of CNN and its mathematics, right? And with stochastic games, okay, it is also an interesting topic because whenever you repeat, right, certain instances, then it is stochastic. For example, outcome, it depends on skills only, okay, as well as it depends on luck also. So if you, whenever you play ludo, whenever you play cards, whenever you play dice, okay, backgammon, which I have not played, okay, gambling, all gambling games, okay, so they are unpredictable in nature. Okay, these unpredictable games are called as stochastic games. Fine. So like for example, here when you flip a coin, okay, you may get a head or a tail. Okay, possibility or chance is 0.5, right? So if you just go through this, so here one more point is added, 0.5. Okay, this is chance. In stochastic game, you have another component called as chance. Fine. So here, as we do always, right? So here it is max. So among 4 and 6, 4 is chosen. Among 9 and 6, 6 is chosen. Among 4 and 6, right? So because it is 0.5, right? So 4 plus 6 divided by 2, it is a chance, right? So and hence you get a 5. Similarly, here 2 is chosen, here 1 is chosen. Then it goes to 2 plus 1 divided by 2 because it is 0.5 probability, okay, with chance. So that is the difference here. So you get 1.5. And among 5 and 1.5, you get 5, right? So accordingly, that node is chosen. Fine. So the topics like stochastic games and Monte Carlo tree search, the importance, if you can give this much, is sufficient. Constraint satisfaction technique. Okay, CSP problems. We are going to talk on constraint satisfaction. Somebody has unmuted or what?
Yes, someone by mistake must have done it. I've handled that.
Husaf, you are saying something?
Yes, ma'am. I said someone might have
Okay,
unmuted
okay.
themselves.
Fine,
Yeah,
fine,
I
fine.
have muted them now.
Okay, okay. My voice is clear, no? No trouble, right?
Yes, yes, it's clear, ma'am.
Okay. So, so because I wanted to elaborate all the topics, I'm just rushing through. Okay. So now constraint satisfaction technique. So we solve a problem with some rules. Okay. So in that case, we call this as constraints. Constraints are some rules you have, certain constraints you have. Okay. So here there are some components you need to remember: X, D, C, right? Set of variables, set of domains. Like for example, if you take 5, it is a number and it is an integer domain. Okay. Also, you will have some set of constraints. Okay. So these three things you will have to remember. Generally, it is a form of depth first search only. How to backtrack and all. Okay. So let us see an example. So before this, I'll go to this. Okay. When you go for graph coloring problem. Okay. So graph coloring problem, we all know that nearby cities will not have the same color. Okay. That is called as graph coloring problem. So just quickly switch over to this. So it takes some time for switching and switching back, but it creates a lot of interest with the students, and hence I always prefer to have switching and switching back. Okay, so again, I've taken an Excel sheet. So what the problem here I want to say is we have this one, right? City problem. So let us assume you have 4 cities, 1, 2, 3, 4. Okay, and in this we want to let you just assume a rectangle. Okay, 1, 2, 3, 4. We want to have red, green, blue, but they should not be together. That is the only constraint. Okay, so the problem is you have 4 cities. Okay, like this. Okay, let me show it like this. Okay, so here let us assume you have city 1, here you have city 2, this edge, this vertex. Okay, so this is 3 and this is 4. Okay, so let us assume this as your problem, right? So you have city 1, city 2, city 3, city 4. Okay, so what you have to solve now is you have V is equal to 1, 2, 3, 4 vertex, right? And you have domain as red, green, blue. Okay, when you have domain as red, green, blue, city 1 and 2 should not have the same color. City 1 and 3 should not have the same color. City 1 and 4 should not have the same color. Okay, 1 and 4 are connected, you assume, right? And 2 and 4 should not have the same color. 3 and 4 also should not have the same color. Okay, so that is the graph coloring problem. So how to solve this? You assume that you have a line here. Okay, I'm not able to draw a line here. Okay, so again, if I stop sharing, no, it will take time. Okay, I will draw it on a Jamboard and show you otherwise. Okay, so now here, how to solve the problem? So you have 1, 2, 3, 4 as cities, right? You have 4 cities. Let us start the problem like this. I am going to assume the first vertex to take the domain or color red. Okay, so meaning is the first vertex is having a color red. Okay, then what will be the color of second vertex? What will be the color of second vertex? It can be, just put it like this. Okay, so second vertex can be green or it can be blue, right? Because you have, how many colors you have in your domain? You have red, comma, green, comma, blue, right? So you may have, suppose if you fix up one as red, okay, then 2 can be the other 2 colors, green or blue, right? And 3 also can be same, right? Green or blue, because anyhow it is not going to affect, right? And similarly, your 4 can be green or blue, right? Right. So now let us move to the second vertex. Assume that your second vertex, you want to fix it with green. Okay. Okay, first you fix it with red. Okay, so I'll just temporarily I'll draw like this. Okay, so second vertex you want to fix it as green. Okay, second vertex you want to fix it as green. Okay, it adjacent color or not, you are able to satisfy the constraint, right? Okay, so now here R prevails, continues, and here 2 will be now green, right? And what will happen to 3? 3 can be, can 3 can be green? No, right? Because already you are given green. So 3 should be blue, right? Red, green, the remaining possibility is only blue you have, right? Or because 3 is here, right? So 3 can be, can somebody say me? What will be the color of 3? All right, so it will go with blue, right? So now here, what will be the color? So now red, green, and blue, right? So now what will be the color here? There is a problem now, right? So because you cannot have again blue. Already you have blue here, you cannot have blue here because they are connected, right? So constraints are there. Then in that case, you need to back propagate. You have to go back from this place to the previous place. Okay, back propagation has to happen here. Okay, so when you back propagate, you may solve the problem. Okay, you may solve the problem. So how to solve the problem? You go back here, check out what is the color. Okay, blue. If blue is converted into green, okay, what will happen? Then again you will go back, change this color, right? So I'll go back to the presentation. You will get an idea. So okay. So this is what we were discussing, right? Graph coloring problem 1, 2, 3, 4, red, green, blue. You had constraints. One should not be same as 2. One should not be same as 3. One should not be same as 4. 2 should not be same as 4. 3 should not be same as 4, right? So those were the constraints. So when you started the problem, you started with red, then you started with green, then here you got a problem, right? So you could not fix up the problem, okay, because they were together, same, right? So then you stopped it and then you backtracked and then you fixed up, like here you can change it as green. Again you need to backtrack and change the previous colors. Okay, so like this the problem goes on, okay, till it fixes with the constraints. Okay, so this is also an interesting problem with constraint satisfaction. The second problem is your crypt arithmetic problems. Okay, so just keeping a value like cent plus more is equal to money, how to get it? So then you need to work on some different constraints and all. Okay, like for example, just a minute. Okay, so now here assumption is like when you carefully observe, you can see there is a carryover here. Definitely even though maximum value you have as 9 and 9, 9 and 9 you cannot have because S is 9 means M cannot be 9. Okay, so maximum one digit number is 9 and 8. Okay, so 9 and 8 if you add also you will get 17, right? So carryover will be M. M is 1 then, right? So you fix up, you start like this. Okay, so S plus M generates a carry which can be only 1. So like this it goes on. So crypt arithmetic problem with its constraints, like same number should not be repeated for different characters. Okay, so with all these constraints you can solve the problem. Okay, I'm leaving to you for further exploration. One step I have said you, right? Similarly, you can solve problems of Sudoku and n-queen problems. Okay, so this video I kept for your understanding. You may play it later and see. One step I'll just show you. This is like Sudoku's 9 by 9, right?
It starts with some squares filled in. It's the player's job to fill in the rest, obeying 3 rules. Each number may only appear once in
So
each
the
row.
constraint is it should not repeat. Okay, so inside 3 by 3 it should not repeat.
And each 3 by 3 grid called a unit.
And inside the complete 9 also it should not repeat.
Before we try constraint
So the thing is, like brute force generally it is followed, which is very complex.
Method goes row by row, trying each possible outcome until the solution is reached. In this example, we'll start with the first
So like
square,
this
the
it
first
is.
row, the first available number, 1.
So you
We
try
then
with
move to the
1.
next square, try the next available number, 2. There's
You try
another
with
2 in the
2.
same row, so it can't fit. We then try the next number, 3, which also fails because there's already a 3 in the row. The next number,
Already it is 2 is there, so it is changed now, right?
We assign 4 to that square and move to the next empty one. We try values starting
So
with
again
the
2
lowest
is
of
there,
these
right?
numbers and
So we
eventually
change
use
it.
5.
So again 3 is
This
there.
process
You
continues to
you
reach the base of the
continue.
row
Okay,
until we
brute
find
force
the
it is.
There's a
Okay,
problem.
so
The only available number in the last square is
so much
9.
complex it will
Complex
go.
because there's another 9 in that column.
So
We must go back to the previous square and try a different value, and then move forward and try again. This produces another conflict because 8 already exists in that column, so it must go backtrack even more.
so we need to
This
backtrack.
continues until the entire puzzle has been solved. If we compare the first row with the solution, we can see that the first attempt failed to place any numbers in their correct spaces. This is the problem with brute force techniques.
So how much
Although
it
they
goes?
find a
9
solution, it
9
requires
cross
searching
9
all possible
puzzle.
outcomes, which will take a
600
very long
million
time.
steps has
In
been
the worst
taken.
case, it would take over 600 million steps to
So
solve
and
the 9
hence
by
it
9
is not advisable.
In
So
order
you
to
need to
speed
have
the
some
process up,
constraints.
We need a way to eliminate large portions of the possible outcomes that we know violate the rules. This is what the constraint satisfaction technique does.
So now comes the
Constraint
constraints.
satisfaction problem is defined by
So we
3
keep a
fields, list
constraint,
of
only
variables,
one
in this case,
occurrence of a
81
number
squares,
in
a domain
each
for
row,
variable,
column,
in this
and
case, the
unit.
numbers 1 through 9, and a list of constraints, in this case the 3 rules of the game. To solve the problem, we need to define what a solution is. For a Sudoku problem, a problem is complete when every variable has been assigned a value and none of them violate the constraints. The search process is sped up by narrowing down the domain of each variable. Take this square, for example. Because of the predetermined
So if you
values
see
of
here.
row, column, and unit, its domain is reduced to just 4 because all the other values are taken.
Okay.
Thus, the value is found for the square without doing any searching. This method is further improved on by updating each affected square after an update. In the previous example, 4 would be removed for the domain of any related squares.
Okay, so you remove the 4 from all the selected squares, right? So row, column, and diagonal, you remove the 4.
The solution is arrived at much quicker using
So,
constraint
when you
satisfaction to
keep a
regulate
constraint, then it is useful. Okay, that is what this small video says. Okay, so you may show some interesting, simple 1 minute, 2 minute videos for the students. They will understand it quickly. Okay, so in n queen also you have a problem. Problem is the constraint is no queen should be placed either diagonally in the same row or column. So if you are able to backtrack and again keep the queen in proper place, then the problem is solved. Okay, so you try keeping in first row, first column. Okay, second queen in second row, but not in second column because it will be diagonally hitting. So you will move to the next row, right? Next row or next column also, right? So the problem goes on. So we call this as like constraint propagation. Okay, so using the constraints to reduce the number of legal values of a variable, which in turn can reduce the legal values of another variable. Okay, so this constraints gets propagated. So some of the case study like Prasad Madam, she said in unit it is given the amazing use case of becoming a fully sustainable business with respect to Google. You can go through it. Google, because of its size of servers and workstations and data centers, the heat dissipation and how they are trying to bring the business as a sustainable business. A case study is given, which is not in this is not for exam, right? So for only to create interest, you can talk to the students. Okay, so to summarize, we have discussed all these topics of unit 3, and I'm just moving to unit number 4. Unit 3 is having a lot of problems and algorithms. Unit 4 is like quite simple. Only agents. On agents, as Prasad Madam, she has touched, I'll just move towards Oneplus world. Okay, so why this unit is important is whenever you want your agent to learn something, okay, especially natural language processing, then this comes as a big support. Okay, so possibilities of exam, I'll just go through it, and possibilities of some logics, right? So we want to represent the world, that is the idea. Okay, so how to represent the world, how to reduce inferences. Okay, so this diagram, as you all know, it was there in the first speaker slide also, right? So with environment, with inference engine, with knowledge base, with learning, what happens? Okay, so what happens here? Okay, so this is called as a Wumpus world problem. Wumpus is a giant which will kill us. Okay, so you start here, you are there here, starting position. Okay, so this environment is like you have 4 by 4 cross matrix. You are starting from the first square. The Wumpus which is going to kill us is in this place. Okay, in your third row and first column. Okay, so whenever you win, you have to take this gold. You have to move from here, go and take this gold here. GOLD here it is mentioned, gold. Okay, so then you will get gold. Suppose if you die because of Wumpus, then you will lose your points, minus 1000. If you get gold, you will get plus 1000. Every step minus 1 is there. Okay, and when you use arrow, then minus 10. Okay, so just come to here, environment, squares adjacent to Wumpus or smelly, squares adjacent to pit or breezy. So you have pits also here. Okay, so whenever you go to the pit, it is dangerous. Okay, so you cannot come out, so you should avoid pit. And there is a point given here, near the pit you will have breeze. Okay, when you get into a square where you can feel breeze, then you can understand there is going to be a pit. Okay, so in this Wumpus world, there are because we are talking about agents, I'm not touching about the basics because it is covered in the first part, right? So what you have to understand is you have sensors, you have actuators, like you have self-driving cars, which has cameras, right? Now you have radars. So you can see, you can perceive, and then you can act on it, how to increase the speed, okay, brake, turn left or right, where the stone is, you act on it, right? Similarly here, so there are some actions, left turn, right turn, forward, grab, release, shoot, sensors, you know, stench, breeze, glitter, bump, scream, right? Okay, now here, how to characterize this Wumpus world? Okay, is it fully observable? No, only local perception. When you are in a one particular square, in your starting square, you can see this and this only. Okay, nearby, local perception only, partially observable. Is it deterministic? Yes, you know outcomes, what will happen. Okay, so if you go here, breeze, then you know that there is going to be a pit. Okay, you know this. So here it is mentioned in environment, squares adjacent to pit or breezy, squares adjacent to Wumpus or smelly. You know the environment. Okay, you know the environment. Means you know means the agent. Okay, when I say you means the agent here. Okay, so glitter if gold is there. Okay, when you shoot, it kills Wumpus, right? So is it episodic? No, sequential. You need to go sequentially and perform each and every action. Okay. Is it static? Yes. Nobody is going to move. Wumpus is going to be in that square. Pits are going to be the same. Okay. Is it discrete? Yes. Is it a single agent? Yes. Okay. So now, so with this Wumpus world, we will be connecting this proposition logic and first order logic. Okay. So how to move ahead? I'm going to connect this. So when you say logic, you have proposition logic and first order logic. Proposition is very fundamentals, foundation. First order is little more expressive. Like for example, here if you see, you have something like PQ, some symbols, true, false, some things, wrapping parenthesis, and or etc. Okay. And if you see here, P and Q implies R. Okay, you can have something atomic sentences for P and Q. If it is hot, if it is humid, then it is raining, meaning. Okay, so P can be anything. Okay, if it is a bird, if it has wings, it can fly. Okay, so like this. Okay, so if it is humid, then it is hot, it is humid. Okay, so like this small sentences, how to frame it as propositional logic sentences. It's a very simple logic. Okay, so these things you can go through it later. Okay, I'll come to the major part, truth value and all. So here you can see like it's hot, it's humid, it's raining. So there are 3 atomic sentences. Like, so I can frame a truth table 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay, so these are all like, because we know, you know this, right? So like these all things are also there. So suppose if your roommate comes to your home, he's completely wet. Okay, so then you will understand like sprinkle was there, umbrella was there or not. Can you conclude the sprinklers are on or not? Okay, so some some understanding, some inference, some deduction of facts. Okay, so it is represented like this: roommate is wet, roommate is wet because of rain, or roommate is wet because of sprinklers. Okay, so roommate is wet because of sprinklers implies sprinklers on. Okay, it is not off, it is on. Roommate is wet because of rain, roommate is not carrying umbrella. Okay, not. Okay, so like this we are trying to write. Fine. Okay, so we are trying to create a knowledge base and come to some conclusions. Okay, so so in exams, some statements can be given like this, and they may be asked to write some statements, right, using propositional logic, some inference. Okay, some BNF, Backus-Naur form grammars. Okay, so we know the semantics of it. Truth table we know, so I'm not going in detail here. So this we know, right? A, B, not A and B, A or B. A implies B. Okay, this is a tricky part. So false, A implies B, right? False, false. A is false, B is false, then answer is true. Okay, so false implies true, then it is true. Okay, so true implies false, it is false. True implies true, it is true. Okay, so what comes as B? Okay, have to check. False and false is true, right? So this is very important, tricky part when you solve. So some theorem proving, some small example we'll see. Because this I have explained you already. Some more examples are there. 2 plus 2 is 4. The sun is cold. Okay, some compound expressions and all. How to form complex sentences. Okay, so you may have negation, you may have or, and, implies. Okay, some operator precedence. Fine. So let us go directly into solving some problems. Okay, so simple one problem will solve, and some of the logical equivalence also you need to know, because to solve this is important. So alpha and beta equivalence is beta and alpha. Okay, so we know that, right? And alpha or beta equivalence is beta or alpha. This also we know, right? And some of this is commutative law, right? And this is associative. So associative is what? You will have alpha and beta, sorry, and gamma. So alpha and beta and gamma. You can see the parenthesis change, associativity, right? So these all rules we need to know. Okay, so double negation. Double negation means negative symbol will move out, right? And see, alpha implies beta. So then if you have negative symbol, negative beta, then implies negative alpha. This is called as contraposition. Okay, so these all rules which the students would have studied in their discrete mathematics. Okay, so just you have to make a quick revision. Okay, De Morgan's law, they know it, right? So negation symbol comes inside and becomes or. Okay, De Morgan's law. So then distributivity with and or. Okay, so mostly when you start a problem, this is very important. This implication elimination. Okay, whenever you have some problem with implication, we need to remove that implication. Okay, so alpha implies B. How to remove this implied is simple. This symbol can be removed by negating alpha and making or beta. Okay, remember this. Like for example here, with resolution solve this. Q is okay, P or Q. Okay, and you have P implies R, Q implies R. You have to prove R. Okay, so P or Q is given. Okay, so negation of P or R is also given. From implies I have changed it. Okay, so then negation of Q or R is given. Okay, from here I've changed it. And because I said you, right? Here, this one. P implies R, implication to remove, we had a rule, right? So you have to negate this P or this R. Okay, that's how it has come. Fine. And then
Excuse me,
negated.
ma'am.
Yeah.
Sorry
Time
to
up?
interrupt. It's 10 minutes are remaining,
Yeah,
ma'am.
yeah. Okay. I'm consciously watching time, right? Okay.
Yeah.
Fine. So I think this is understandable. Similarly, one more problem is solved. You can go through it. Okay. So then first order logic also, it is like more advanced than propositional logic. You have some interesting things like existential quantifiers, universal quantifiers, okay, where you will solve some problems, right? So here, for example, all man drink coffee. Then how to write it? For all x, where x is a man, implies drinks x comma coffee. So whenever there is a predicate, you have to put it inside. So x drinks coffee. Okay, so then it will be easy. So some boys are intelligent, some only. So then it is an existential quantifier. So there exists an element x where x is a boy and he is intelligent. Okay, use and symbols, etc. Right. Okay, so all these things you can just go through it. Some case study is given, which will help you, right? So with this, I think I'll close this. Done, right? Thank you, all of you.
Thank you so much, ma'am.
Yeah,
Yes.
I was thinking like whether I will be able to do it.
Okay, ma'am.
Thank you.
So
So I had a thank you slide. I think because of your pressure, I missed it. Just a minute. Allow me to share this. I wanted to
so,
thank
so,
few people.
so sorry for that, ma'am.
Yeah, no, it's okay because as a some quick questions I just drafted because it may help you. Like min max is ready to teach. All these things I'll share it with you. It's okay. Just I wanted to share my presentation once more. 1 second. One second.
Sure, ma'am. Meanwhile, dear faculties, if you have any questions, we can take up those questions for Rajeshri ma'am now.
Rajeshwari.
Yeah, yeah, Rajeshwari ma'am. Yes, sorry.
It's okay. Okay, so I just wanted to acknowledge my faculty fellows here, Mrs. Pallavi Dade and Miss Santwana. They helped me because they are handling AI here. We had nice discussions. The result of this presentation, 14 hours, I could do it because of their support for me. And I thank Dr. Vivekanandan who helped me in identifying some good videos. Dr. Uday Patkar for giving me an opportunity to be here. It's really wonderful to meet so many faculties here. Prasad Madam and Madhavi Pradhan Madam, we were together for syllabus and discussions. The order, what I have written is from lower to higher. So I thank my sincere thanks to Varsha Patel Madam. Because of her, we always feel proud to be a part of computer engineering department. And all the things, streamlined things. And I am double happy because she is a lady. So no role model she is. Thank you very much, Varsha Patel Madam, for all your leading examples. And some of the web resources I want to thank. And as already shared, like Russell's book is available online also. You can take out, and I have taken few of the material from there, most of the material. And CSE IITD is a good place where you can get many of the good contents, and Java Point also. Okay, so I've kept bumpers only, whereas many of the resources are available here. Okay, so thank you very much. Thank you, all of you.
Yes,
Done? Is it
thank you
done for me?
thank you so much for that, ma'am.
Thank you.
That was a wonderful practical session, I would call that. So yes, respected faculties, if you have any questions for ma'am, you can please put it in the chat box, or you can even unmute if you would like to. We'll wait for a couple of minutes. If there are no questions coming in, then we will be leaving for a lunch break,
Okay, fine.
and we all will meet again at sharp 2:10. So we
I,
can begin with the session between 2:10
yes.
and 2:15.
Yeah, yeah. So people, because they have not asked me any doubts, if you wish to contact me, you can contact me. So for any support, kannan.rajeshwari@pccipune.org, or contact me through my mobile number. And slides, you can get it from Uday Patkar sir. Okay, thank you very much.
Yes, I think yes, there are no questions coming in because the
Yeah.
session was so
Yeah.
beautifully explained. So
I have a
I,
question.
oh yes, yes, please
Yeah.
go ahead, ma'am.
Yeah. First of all, thank you, ma'am. Thank you so much for this informative session.
Thank you.
Yeah, ma'am. Actually, Monte Carlo tree search. I was seeing the third and the fourth edition. It has been
Okay.
added in fourth edition, but fourth edition
Okay.
is not accessible to us.
Oh, is it so?
Yeah.
Even I could not access actually. I took it from many resources I found. Some interesting examples I saw, but it was away from the scope of third year
Okay.
students.
Yeah.
Okay,
Yeah.
so even some
Okay.
mathematics, some expressions I saw. So if you can cover this much, it is sufficient.
Okay. Okay.
Okay.
Fine.
Other strategies of game playing can be given more importance.
Okay. The alpha, beta, and the
Yes,
min
madam.
max.
Yes, madam. Yes,
Yes. Yes.
constraint
Okay.
satisfaction problem and all.
Constraints. Okay.
Yeah,
Okay.
and
Thank you,
like
ma'am.
they said, na, like small projects to give and to develop is also a good idea.
Yes, ma'am. Okay.
May I know
Yeah.
your name, madam?
Ma'am, Amruta Tandole from PICT.
Fine, madam. Thank you.
Yeah. Okay.
Fine.
Yes, thank you for your
Thank you.
question,
Thank
ma'am.
you.
Are
Bye bye.
there any more questions coming in? Okay, I think, ma'am, that'll be it for your session.
Yeah.
So thank you so much, ma'am, once
Thank you
again.
very much. Thank you. Bye.
And yes, now, respected faculties, we'll be going on a lunch break and see you all at 2:10 sharply, so we can begin with our third